Okay, so thank you for the invitation. It's a pleasure for me to be here and to have the opportunity to talk about the current status of the evolution of massive stars, what we know today, and hopefully which will be the future directions in this field. Massive stars plays a important role in the evolution of the universe for many reasons, but in this context specifically we are interested because they are connected to the gravitational waves. So having a good knowledge of the evolution of these stars is important for many reasons. So in the following I will present an overview of the evolution of these stars as a function of metallicity, mass, and rotation. And then in the second part of the talk, I will address some uncertainties affecting the stellar models. All the models that I will present have been computed with our code, the Franek code, in which we consider all the equations. Here. Okay, all the equations for the structure of the star, the chemical evolution of the matter due to the nuclear reactions, mixing for many species, up to 300 and even more, and also the equations for the angular momentum transport. And we couple all these equations together and solve them simultaneously. So let me start with the showing the evolution of a typical massive star. This is a 15th solar mass star. This panel here is the Kippenham diagram, where you have the time on the x-axis, the interior mass of the star. The colors refers to the chemical composition. So we have hydrogen-rich material here, helium-rich material here. Red means carbon-oxygen-rich material, and so on. The green areas correspond to the convective zones. So you can see here the hydrogen and helium burning phases here occurring in the convective core. The first dredge up occurring here when the envelope penetrates into the star and dredges up the material produced by the hydrogen burning. The carbon-oxygen core here formed after the core helium burning. Then carbon burning occurring here in a convective core, and then proceeding through a formation of a number of convective zones. Neon burning, oxygen burning occurring in the center in a convective core here. Oxygen burning following then with the formation of the oxygen shell. Then core silicon burning, shell silicon burning, and the formation of the iron core. This complex behavior, interplay and timing among convective zones and nuclear burning shells produces this stratification of the chemical composition of the star at the time of the collapse, where you have the typical onion structure, where each zone, so you have an iron core surrounded by zones with different composition left by the various burning occurred either in the center or in the shell. This panel here shows the evolution of the star in the HR diagram, so the surface evolution of the star. And what is important to note is that when the star becomes a red supergiant, it enters a phase of very strong mass loss due to the formation of dust, the so-called dust-driven wind, where the mass loss increases even by 1 order of magnitude. But in this case, this phase is reached at the very late stages of helium burning, so there is not much time for the star to lose enough mass in the following stage. So this star explodes as a red supergiant. This is a typical temperature and density structure of a red supergiant star at the time of the explosion. So if we increase the mass of the star, the mass loss becomes much more important. So for example, here in the 20 and 25 solar masses, The dust-driven wind phase is achieved at the early stages of the core helium burning, so there is a lot of time for the star to lose mass, and as a consequence, these stars become blue supergiant, Wolf-Rayet blue supergiant, because they lose almost all or completely the hydrogen-rich envelope. For the 60 solar mass star, for example, here, the red supergiant phase is skipped because this star reaches the Eddington luminosity before becoming red supergiants, and so the mass loss is not driven by the dust, but is driven by the approaching to the Eddington luminosity. And the final result is that the total mass, the total hydrogen mass of the envelope, and even more, is lost by the star, exploding as a Wolf-Rayet blue supergiant. These are the Kippenan diagrams of these stars, and you can see the strong mass loss occurring during the core helium burning phase. The evolution of the core is also slightly different in the sense that in general, the higher is the mass, the lower is the number of convective zones formed in the carbon-oxygen core, and this is due to the less efficient, in general, carbon shell burning. Depending on the mass loss history, you may have three different, or a number of different supernova expected. For example, for the 20 solar mass star, we expect a type 2b supernova, because we have a very small amount of hydrogen in the envelope. Type 1b in the case of the 25, and maybe type 1b or even 1c for the 60 solar mass star. Okay, this is the density profile of all these models at the time of at the presupernova stage. You see the transition from red supergiants to blue supergiants progenitors, and the transition is around 20-25 solar masses. So we do not expect, we do not predict stars exploding as type 2 plateau supernovae with mass larger than 20 solar masses. And this is essentially compatible with the observations reported by Smart 2015, in which he did not find any progenitors for type 2 supernovae, type 2 plateau supernovae with mass larger than 20 solar masses. Okay, if we reduce the metallicity, this picture changes significantly, because by reducing the metallicity, we reduce very much the efficiency of mass loss. This is the comparison between solar metallicity stars on the left and low metallicity stars in the right. And you see that at low metallicity, both the 25 and the 60 solar masses taken as an example, they both evolve at constant mass. So the mass loss is essentially negligible. The other thing that is important to note is that the carbon-oxygen core mass for the 25 solar mass is essentially independent on the metallicity, while in the 60 solar mass case, there is a substantial increase of the carbon-oxygen core at low metallicity because of the absence of the mass reduction due to mass loss. So as a consequence, by going to the solar down to the low metallicity cases, we expect a reduction of red supergiants progenitors and the increase of the blue supergiants progenitors. Also, the Wolf-Rayet stars we expect to reduce with reducing the metallicity. As I mentioned before, the carbon-oxygen core mass increases with increasing the mass at low metallicity much more than it happens in the solar metallicity case. And we find that for stars with initial mass, let's say larger than 80, 90 solar masses, the carbon-oxygen core mass becomes large enough that the star enters in the pulsation, in the peri-instability regime. You see here that a substantial fraction of the carbon-oxygen core, in this substantial fraction of the carbon-oxygen core, the gamma decreases below 4/3, and so you have instability, peri-instability. The following evolution in this case is that the pulsations drive some mass ejection before the explosion or non-explosion of the star. So what about rotation? The rotation also changes this picture because the main effects of rotation is that of increasing the cores because of the rotation-driven mixing. The increase of the core means increase of the luminosity. That in turn means increase of mass loss. So you have rotation-driven mixing increasing the core increases the luminosity, increasing the luminosity increases the mass loss. So you have an indirect effect of rotation on the mass loss. So in general, the rotating models lose more mass than their non-rotating counterparts. And this happens also at low metallicity. So you can see that even at low metallicity, stars may lose a lot of mass with rotation. The increase of the carbon-oxygen core also makes some difference with respect to the non-rotating case. At solar metallicity, for low masses, the carbon-oxygen core increases because of the rotation-driven mixing. But for high masses, the dominant effect is the mass loss, even with rotation. So in this case, we don't have an increase of the carbon-oxygen core, but a decrease of the carbon-oxygen core, because mass loss is a dominant effect. At low metallicity, here, you have an increase of the carbon-oxygen core in all mass spectrum, and so you have, as a consequence, a reduction of the limiting mass that enters the pulsation pair instability. Okay, so we may draw a general picture of the evolution of massive stars for each metallicity here, each rotation velocity. We can predict, let's say, as a function of the progenitor mass, which is the final mass of the star, which is the composition of the wind, which is the composition inside the star, which stars explode as red supergiants, which stars explode as blue supergiants, which is the expected limiting mass between neutron stars and black forming supernovae, which we expect them to directly collapse to a black hole, and so on. Even if these models can be used to address and to discuss a number of astrophysical subjects, these models are in general affected by large uncertainties. Not only these models, but all these kind of models available in the market. Because all these models are computed in spherical symmetry. And the uncertainty comes from the fact that you pretend to model multidimensional physical phenomena like convection, rotation, magnetic field in spherical symmetry. And of course, this is a source of uncertainty, a great source of uncertainty. Moreover, there are some physical ingredients in the calculation of stellar models that are very uncertain, like mass loss, for example, as we will see in a moment. And mass loss, as I showed you before, very much affect the evolution of these stars. So in the context of convection, for example, one main issue is the treatment of the so-called breathing pulses. This phenomenon occurs during the core helium burning. And this is due to the fact that during helium burning, the convective core increases in size because of the conversion, because of the increase of the opacity due to the conversion of helium into carbon and oxygen. So at the end of the helium burning, the helium that is ingested in the core becomes comparable with the helium that is present in the core itself. So this implies an enhancement of nuclear energy generation that is not counterbalanced by the stabilizing effect of the reduction of the opacity due to the ingestion itself. So once this happens, the star enters into a phase of progressive increase of the convective core until it stops when enough helium is ingested in the core, and again the stabilizing effect of the opacity dominates over the effect of the increasing of the energy generation. So what is the consequence of this effect? Of course, a prolonged core helium burning phase, because you ingest more fuel in the core, so the star lives more in this phase. A prolonged conversion of carbon-12 into oxygen-16. You see that you have these spikes here, because once carbon-12 is going to decrease during the late phases of helium burning, it is ingested again because of new ingestion of helium. So you have a prolonged conversion of carbon-12 into oxygen. And this also implies a non-monotonic or stochastic, I would say, carbon-12 left by the core helium burning. We don't have any theory based on first principle to treat this phenomenon. And it's not clear if this phenomenon should be present or not in the stars. So we can be guided by the observations, for example. We know, for example, that the number of AGB stars and the horizontal branch stars in the globular clusters is very sensitive to the occurrence or not of the breathing pulses. And the study performed based on the observations of 48 globular clusters in the galaxy concluded that in order to reproduce the observations, the breathing pulses must be suppressed in stellar models. Now, as I mentioned before, the breathing pulses affects the abundance of carbon-12 as core helium burning. And this is a fundamental quantity for the evolution of the stars, of the massive stars, because the abundance of carbon-12 affects the efficiency of the carbon shell burning. And this in turn affects or determines the contraction history of the carbon-oxygen core. A more efficient shell means less contraction, a less efficient shell means higher contraction. And therefore, this directly impact, oh, sorry. How can I go back? Yes, this way, no. Okay, so this impact directly on the compactness of the star. This is shown here in this plot. You have two models of the same mass, but with two different abundance of carbon in the carbon-oxygen core. And you see that these stars at the presupernova stage have a very much different compactness. And this is due to the different carbon-12 abundance. Another issue, still in the context of convection, is the carbon-oxygen shell merger that can appear during the very late stages of massive stars. The ingestion, again, the ingestion of carbon in the oxygen-rich layer implies a burst of nuclear energy that drives an expansion of the overlying layers, and this obviously directly impacts on the compactness of the star. Now, the problem is that this is not found systematically in 1D stellar models. It is not clear whether this is a numerical issue or if it is expected to occur in real stars. And of course, this leads to a stochastic behavior of the compactness as a function of the progenitor mass. Recent multidimensional simulations of this very short phase actually found a very different behavior compared to the 1D stellar models. But I have to say that this is not a conclusive result, because in this study a very small nuclear network is adopted, and this is crucial for the calculation of the energy generation, and also because it has been performed on only one model. Of course, still much work should be done in this respect. So all these differences can explain, but of course I'm not sure, but could explain the differences that we found between different sets of stellar models. This is an example, the comparison between our stellar models in red and Sukbo's models in black. And you can see a different carbon-12 relation at core helium depletion. We find a much more tight relation of this quantity, and this directly amplify to a very different behavior of the compactness. It is due to the treatment of the Britten pulses or to the carbon shell merger, I don't know, it's difficult to say, but you can see here that this very small scatter gives a very strong scatter in the compactness parameter, while a very tight relation here gives you a very well defined trend, even if it is still non-monotonic. Another important issue is the treatment of convective core overshooting during the core hydrogen burning. This was initially invoked in the 80s to explain the main sequence band observed in association of massive stars. And the reason is that we expect that convective elements penetrate because of the inertia into the radiative layers. But again, we don't have any theory to treat this. But convective core overshooting in core hydrogen burning has a strong impact on the evolution of the star. This is a comparison between two stars with and without overshooting, and you see a very different total mass at core hydrogen depletion. In this case, the black line with overshooting loses more than half of its mass, slightly less of half of its mass compared to the red line. So after core hydrogen burning, before the core helium burning, another instability occurs in the region of variable chemical composition left by the core hydrogen burning. This region becomes stable according to the Schwarzschild criterion, and unstable according to the Schwarzschild criterion, and stable according to the Ledoux criterion, because the Ledoux criterion takes into account the stabilizing effect of the gradient of chemical composition. This is a well-known situation. It's called semi-convective zone, but again, we don't know which is the velocity, which is the efficiency of convection in this zone, because this zone is treated by means of the mixing length. A different approach can be used using a fast velocity, a slow velocity, and this different approach can produce a very strong final, a very different final result. You see, with the slow mixing, you have a strong reduction of the total mass, while with the slow mixing, with the fast mixing, you have a very slight reduction of the total mass. So at the end, we expect two different outcomes in this case. In one case, we expect a type 2P, 2 plateau supernova. In another case, a type 1B supernova, simply because the mass loss history changes. And this is due not to the final stages, but it is due to a treatment of a phase that goes from the core hydrogen depletion to the core helium ignition, so at the very early stages of massive stars. Finally, mass loss. Mass loss is a crucial ingredient in the evolution of massive stars. We may have different prescriptions in different evolutionary phases, main sequence, red supergiant phase, Wolf-Rayet phase, and so on. The problem is that all these prescriptions cannot be, are not reliable to a precision better than an order of magnitude. So we have an order of magnitude difference. And this has a strong impact on not only on the evolution of the mass loss history of the star, but also on the expected remnant mass of these stars. In one case, for a more efficient mass loss, we expect a smaller remnant. For the higher mass loss, we expect a larger remnant. And both these prescriptions are within the uncertainties. So we may have two different scenarios in which we have, in this case, stars above, let's say, 20 solar masses producing black holes, or stars, in this case, we have an island of mass that produces black holes and an island of mass, even massive, that produces neutron stars, and so on. Finally, in the last few minutes, rotation. Rotation is a multidimensional effect. We want to treat it in spherical symmetry. There are different approaches followed by different stellar evolution codes. Some codes uses an advection diffusion equation for the angular momentum transport. Other codes use a pure diffusion equation. The treatment of mixing is also generally used as a diffusive approach. We can calibrate the efficiency of mixing by means of different observations. The problem is that the two different calibrations that provide a good reproduction of the observed data can give a completely different results. We have a strong tool to check the way in which we treat rotation, and this is the astroseismology. Kepler provided the rotational, internal rotational velocities for a number of red giant stars, and with the best that we can do now, we are not able to reproduce the internal profile of the angular velocity of these stars. Situation does not change even if we include magnetic field. Still, we are far from the observations. Few slides more, but I am concluding. Of course, future directions would be to develop 3D stellar models. This is not possible at present because of the very different spatial scales and time scales that are relevant for the massive, for all the stars. Probably we may find new strategies, new methodologies to put together 1D stellar models and very short phase 3D stellar simulations. Okay, I'm finished. Thank you for the attention.
Questions?
So you tell us a 60 zero-H main sequence star loses mass and ends up as a 5 solar mass naked helium star? How?
Not during the main sequence star, during the Wolf-Rayet stage.
Okay.
During the Wolf-Rayet stage, as I showed you before, this is not, how can I, okay, let me go this way. Okay, so here, this is the core helium burning phase. So two different prescriptions for the Wolf-Rayet mass loss, still in the range of the uncertainties, produces a very strong difference.
Is there any observational evidence for either one of the scenarios?
There is some observational evidence, but they are not conclusive, because you can, in general, you try to reproduce the number ratio of Wolf-Rayet stars in the galaxy or in the Magellanic Clouds in different stages. But this is not conclusive because you must incorporate this in a synthetic models that takes into account the evolution of the galaxy, so taking into account star formation rate, IMF, and so on. And this is not done yet.
So I have a question on the mixing and the path forward on this, because it's a really daunting problem. That you already mentioned, the 3D models are limited. You know, they don't have the full networks. They actually have boundary condition issues. I assume this is going to be an iterative process, but from you, I was thinking, how do we best approach this? How do we identify the key problems we need to solve, then try and do better, and then iterate and, you know, get better recipes? Do you have a plan on how we're going to move forward on this?
I am honest, I don't have plan because I have no expertise in multidimensional simulations. This is something that I ask to you that are expert. So probably we can keep in touch to develop something together. But what I wanted to point out is that the differences, I mean, the phases that should be studied are not the final one, that of course are important, but the difference comes out at the early stages of the star. For the longer phases, hydrogen burning and helium burning, these are the phases that should be studied, but I understand that it's not possible.
Identify, you know, if we can identify the phases we need, you know, that are most crucial based on the 1D, and people are doing this. It's not like it's not being done, but I think this will make the progress be more, I think, effective.
Okay. One more.
And just to add to the discussion, obviously, as you said, Marco, you know, we may identify, say, two phases, for example, that are crucial, and to actually simulate one of those two phases may be impossible at the moment, whereas maybe to you know, simulate the other, or at least, you know, have some start on simulating the other. So I think, you know, even just identifying, you know, something that is potentially addressable in the nearer term with a longer term plan of addressing some of those other phases later would be extremely helpful, because as you know, what we've done is, in fact, we've focused on the late stages only, right? The very late stages, you know, silicon burning, you know, for example. And already we know from that alone that the outcomes in the models have been qualitatively different, not just quantitative, but qualitative. And if you're saying that the more important, potentially the more important phases are earlier, then that's even more pressing. So yeah, if we can identify, we need to go, as you and I were discussing, right, walking together in the park, we have to go backwards. Right?
Yeah.
And how far back can we go, you know, but still be realistic?
Okay.